When people talk about 6G, the discussion usually focuses on faster speeds, new spectrum, or futuristic applications such as holographic communication. But there is another major transformation happening behind the scenes. The cloud infrastructure that runs mobile networks is also evolving dramatically. Future 6G networks are expected to combine AI, cloud computing, distributed computing, automation, satellites, edge computing, intelligent radio environments, and autonomous orchestration into one unified platform. Some of these technologies will be highly visible to users while others will operate quietly behind the scenes. Both are equally important. In this video, we will look at some of the key visible and invisible technologies that could shape future 6G networks. To understand where we are heading, let us briefly go back in time. In early mobile networks, most network functions ran on dedicated hardware appliances. Every function often needed specialized proprietary equipment. Then came network functions virtualization, or NFV. Instead of relying on proprietary hardware, operators started running network functions such as software on standard servers using virtual machines and later containers. This was one of the key foundations behind modern 5G cloud-native networks. But 6G takes this much further. Future telco clouds are expected to become AI-native, highly distributed, autonomous, and tightly integrated with edge computing and non-terrestrial networks. We do not yet know all the things that 6G will ultimately entail, but we know for sure that it is not simply about making 5G faster. Future networks may support immersive XR experiences, holographic communication, autonomous systems, industrial automation, integrated sensing and communication, and truly global connectivity. These applications require extremely low latency, massive compute resources, ultra-high reliability, and intelligent automation. In some cases, networks may need to support sub-millisecond latency and large-scale AI processing in real time. This is why the entire network architecture is evolving beyond traditional telecom infrastructure into a distributed computing platform. One of the most important concepts being explored for 6G is in-network computing. Traditionally, applications send data to a central cloud for processing, but for future AI and XR services, sending everything to distant data centers may introduce too much delay. Instead, compute resources can be distributed across the network itself. Processing may happen at the edge, inside transport networks, or even within network devices. Edge computing is one practical example of this trend, bringing compute resources closer to users and applications. The network is no longer just transporting data, it is also becoming a distributed computing platform. Future orchestration systems may dynamically decide where workloads should run based on latency, compute availability, and service requirements. Another major trend is hybrid cloud. Operators increasingly use a combination of private cloud infrastructure, edge cloud resources, and public cloud platforms. However, managing workloads consistently across multiple cloud environments is extremely difficult. Different cloud providers use different APIs, orchestration systems, and operational models. Future telco cloud architectures aim to provide unified orchestration across all these environments. This does not necessarily mean everything moves to public cloud. Future deployments are likely to use the most appropriate combination of private, public, and edge cloud resources. At the same time, AI-driven automation is becoming increasingly important. Future networks may continuously monitor themselves, analyze conditions, and automatically optimize performance without human intervention. This is often described as closed-loop automation or autonomous networking. Another major area for 6G is non-terrestrial networks, or NTN. Future networks are expected to integrate terrestrial infrastructure with satellites, drones, and high-altitude platform systems. Unlike earlier generations where satellites were used as separate systems, 6G may integrate NTN directly into the network architecture itself. This creates many new challenges because satellites and airborne platforms are dynamic and constantly moving. The orchestration system must manage changing topology, varying latency, spectrum coordination, and cross-domain resource management. The goal is seamless connectivity anywhere on land, sea, air, and space. Managing future 6G networks manually would become far too complex. This is why researchers are exploring intent-driven networking. Instead of manually configuring every network parameter, operators define high-level objectives or intents. For example, an operator may specify that emergency communications in a region must maintain ultra-reliable low-latency connectivity. The orchestration platform would then automatically determine the best combination of network, compute, and radio resources. AI systems continuously monitor network conditions and dynamically adapt the infrastructure to achieve the desired outcome. Traditional virtual machines are powerful but relatively heavy. Containers improved efficiency significantly, but future 6G environments may require even lighter approaches. This becomes especially important at the edge or within constrained environments such as satellites. Technologies such as micro-VMs, WebAssembly, and lightweight container platforms are gaining attention. These approaches reduce overhead while still providing strong isolation and security. The result is low latency, better efficiency, faster scaling, and the ability to run more network functions closer to users. One of the more futuristic technologies being explored for 6G is Reconfigurable Intelligent Surfaces, or RIS. RIS consists of programmable surfaces that can dynamically control how radio waves propagate through the environment. Instead of treating the wireless environment as fixed, RIS allows the network to actively shape and optimize radio propagation. This could improve coverage, increase throughput, reduce interference, and improve energy efficiency. For example, RIS panels may help redirect signals around obstacles or improve indoor coverage without requiring additional base stations. Although RIS has attracted significant research interest, commercial deployment remains relatively limited today. In the future, RIS resources may even be dynamically orchestrated as part of the wider network infrastructure. AI and machine learning are expected to become deeply integrated into future 6G networks. AI systems may continuously collect data, analyze network behavior, predict issues, optimize resources, and automate decisions in real time. This could enable autonomous fault management, intelligent network slicing, predictive optimization, AI-driven security, and energy-efficient operations. Rather than humans manually reacting to problems, future networks may increasingly become self-optimizing and self-healing. In many ways, AI becomes the intelligence layer running across the entire network. As networks become more powerful, energy efficiency also becomes critically important. Future 6G systems are expected to focus heavily on sustainability and intelligent resource optimization. AI may dynamically optimize power consumption based on traffic conditions and demand. Unused network resources could automatically enter low power states when not required. Cloud-native architectures and virtualization may also improve infrastructure utilization and reduce hardware waste. The goal is not only higher performance, but also low energy consumption and reduced environmental impact. In summary, when we talk about 6G, we are not simply talking about faster radio technology. We are talking about the convergence of networking, cloud computing, AI, automation, distributed computing, non-terrestrial connectivity, intelligent radio environments, and sustainability. Some of these technologies will be visible to users, such as satellites, high-altitude platforms, smart surfaces, XR devices, and connected infrastructure. Others will remain mostly invisible, such as NFV evolution, telco cloud orchestration, lightweight virtualization, AI-driven automation, and intent-based management. Together, these visible and invisible technologies will shape how future 6G networks are designed, deployed, and operated. Many of these ideas are still evolving, but their foundations are already appearing today in 5G advanced, cloud-native telecom platforms, AI infrastructure, and edge computing. So while 6G may still sound futuristic, Many of its building blocks are already being developed now. We hope you enjoyed this video. It covers a broad range of topics and provides a high-level overview of some of the technologies that could influence future 6G networks. If there is a particular topic you would like us to explore in more detail, please let us know in the comments below. If you found this video useful, please like, subscribe, and share it with others who may find it interesting. You can find links to our websites, blogs, training resources, and social media channels on this final slide and in the video description. Thanks for watching, and we hope to see you again soon. Goodbye.